and we're going to talk about hypothesis test for one population mean, assuming sigma is known. Coming out of previous section 9.4, we actually looked at the same title. The only difference was in section 9.4, the population deviation sigma was known. And in section 9.4, we used the z-test to test our hypothesis. So in this section now, sigma, the population deviation, is unknown. So we're going to see how this is going to be done. Now, because sigma is known, the probability distribution of our test statistic that we're going to look at, it's going to be a t-distribution. Now, we talked about t-distribution actually in chapter 8 when we looked at confidence intervals for almost the same reason, because in chapter 8, when sigma was unknown, we used a t confidence interval. So here we go. Now, as far as, by the way, the things that we already know coming to this section, we already know about significance level alpha, we know about type 1, type 2 errors. So all the jargons, all the terminologies we've already spoken about. In section 9.5, we're just going to see how the test procedure changes ever slightly. So our test statistics in this section is going to be a T, and the author in your textbooks, by the way, he actually uses a subscript, this null subscript here, which is T sub 0. This looks like 0, but this is the null value. Okay, this is the T, assuming the null is true. That's what that is. So our test statistics looks like pretty much like it did in previous section 9.4. The difference is that in section, again, 9.4, we used a z-test. Now we use a t-test. And instead of sigma in here, I have highlighted, instead of sigma, now we have S, standard deviation. So our procedure is going to be a one mean, one sample, one population mean, that is mu, and the procedure is a t-test. So our assumptions are pretty much, the top two assumptions are the same as previous section, that we have a simple random sample with replacement, or we have, we are sampling from either a normal population or a large sample. Now, if we sample from a normal population, this t-test, by the way, will be exact. Otherwise, it's approximation when sample size is large. And remember, sample size large for us meant n at least 30. Correct? At least 30. Now, assumption number 3 here is where sigma is unknown. So when sigma is unknown, the effect is on the denominator of our t-test here. Again, for a z-test, this was sigma. Because we don't know sigma, we're going to estimate it using S, which is the sample standard deviation. And that in turn turns the probability distribution of our test statistic, means this ratio, into a t distribution. Now, the degrees of freedom, by the way, that we need for this t distribution is going to be n minus 1, and that degrees of freedom is right in here. There you go. It's to the left, lower left, right here. So as far as our procedure goes, again, in the case we use a critical value approach, we reject if we fall into rejection regions, depending on whether I have two-tail, left tail, or right tail tests. And these values depend on, of course, the critical values depend on alpha. Okay. Let me fix this one. This should be, this region here is what alpha is. Okay. And in here, this is what alpha is. Alpha is, again, the area in the tail. Okay. And in the case of a two-tail test, remember we divide alpha by 2. And that's why I had alpha over 2. For some reason, in the book, these alphas don't show up. Okay. And if we use the p-value approach, as always, we reject the null hypothesis if p-value is less than or equal to alpha. And again, in these sketches, t sub 0 looks like these are the value of the test statistic. So let's take a look at an exercise here. In this exercise, we're looking at number 101. According to Communications Industry Forecast and Report published by Veronis Schuler Stevenson, the average person watched 4.55 hours of television per day in 2005. A random sample of 20 people gave the following number of hours of television watched per day for last year. Excuse me. So here we have these hours of television watched. So looking at this individual only watched 1 hour a day. And the numbers, of course, are all over the place. They go as high as 9.1. Let's see, 9.1 hours. Wow. This individual watches over 9 hours a day of television, as opposed to the minimum, which is 1. Okay. So I have highlighted the important stuff here for you. At the 10% significance level, remember our significance level is what alpha is. Do the data provide sufficient evidence to conclude that the amount of television watched per day last year by the average person differed from that in 2005? Now remember, when we set up the statement of hypotheses, we look for these keywords. So here are example of keywords: differed from. Now here I have written the summary statistics that were given according to the author of the book, and I have written them here. X bar is 4.76. He calculated the average of these numbers. And the standard deviation is 2.297 hours. So those are given to us. I call those summary statistics. And the sample size is 20. Now, one thing, by the way, if you look at the ratio of a standard deviation, 2.3 almost to 4.76, that's pretty high ratio. And I may have mentioned it, but we have one measure of variability, that's CV, coefficient of variation. That's what this is, which is the ratio of S divided by X bar times 100%. And this ratio turns out to be 48.3, which is pretty high. So what does that mean? It really means that if you think of average, the sample mean, as a typical score, a representative of all the scores, it's really not a typical score in this case. In other words, if you ask someone how many hours of television do you watch a day, you most likely are not going to hear anything close to like 4.76 hours, because the CV is so high, because the variability is so high. The ideal CV values should be less than or equal 5%. So this is just on the sidebar. This is not part of the exercise or anything. It just caught my attention, so I thought I make a comment about it. So let's go back here. The null hypothesis is that the mean is 4.55. Remember, that's how many hours of television was watched in 2005. So we take that to be the status quo. So the null says this year is, or last year is, no different than 2005. Against the research hypothesis, the researchers want to know if it's different from this. So the alternative is going to be not equal to 4.55. Now, we need to calculate our test statistic, and I did. The value of our test statistic is going to be 0.41 once you do the fraction. Okay, and I did. Hopefully you can follow the arithmetic. I did the numerator first and divide by the denominator. Okay, so what I have here is the distribution of individual viewing times according to our assumption that data follows a normal distribution. And the center of distribution is 4.55, which is the presumed value of the null hypothesis. Remember, we always assume the null is true. So if the null is true, that's where we're getting our sample of individual viewing times from. The deviation in the population is approximated to be 2.297 because we're using the sample to approximate it. So The t distribution is going to have n minus 1 degrees of freedom that we're going to use. That's 19 degrees of freedom. And our critical values, we can find our critical values independent of our data. In fact, we don't even need to collect data in order to find critical values. There are two pieces of information that we need in order to find the critical values. The two pieces of information are the significance level alpha of the test and the direction of inequality in the alternative, in this case not equal to. Now, how did I calculate this plus minus 1.729? Let me actually show you. So I went to StatCrunch. For t-tests, by the way, everyone, for t-confidence intervals and t-tests, we rely heavily on the StatCrunch, okay? Especially for p-values of hypothesis tests. If it's a t-test, we cannot even find t-values exactly from the table in the back of your book. So we have to use the StatCrunch. And I'll show you how I got these numbers in a minute. But our critical values are plus minus 1.729. So as you can see here, I have the rejection region here is going to be to the right. So this highlighted region is the right rejection region, and this part is the left rejection region. This is actually a t-distribution, what you're looking at here. This is a t-distribution with 19 degrees of freedom. Sample size minus 1. That's what that is. Okay, so how did I get these numbers? Well, in order to have, for the two-tailed test, alpha was 10%, so I want 5% in the upper tail and 5% area in the lower tail. That leaves us with 90% in the middle, doesn't it? The red zone is 90%. So that's what I have. I went to StatCrunch and I looked at the probability calculator. And if you note here, I have the probability is 0.9 at t with 19 degrees of freedom. So let me go to StatCrunch and actually show you how I've done that. And here's the StatCrunch. So let me X out. So you go to Stat, then you go to Calculators, and we go down to t. Okay, let's change our degrees of freedom to, for this exercise, to 19 degrees of freedom. So I'm gonna do that here, and here's 19. Now, what I did is I went to between, and I changed this probability to 0.9, 90% between. So again, in order to have 5% on the right tail, 5% on the left, that leaves us 90% in the middle. So this is one way to do it, and we get those two critical values, plus minus 1.729. The other way you can do this is you actually find the value in one tail, and then use symmetry and reflection to get the other one. So here's what I mean. You can go probability of less than, you want the area to the left to be 0.5. which is half of 10%, because this is a two-tailed test. You have to divide your alpha by 2. Otherwise, you're not going to get the right answer. And there you have it. So we got the number negative 1.729 again. And by reflection, you get the upper tail. Or you can just change that to greater than equal to, and here's 0.05 on the right tail. You get the other critical value this way. So I think the way I did it was reasonable. I went 90% between, and that gave me the two in just one run of the StatCrunch. So what is our decision here? 0.41 does not lie in any rejection region, the highlighted regions, so we do not reject the null. And our conclusion is that the TV viewing times on average haven't changed since last year. Okay. And this is the actual StatCrunch run of this exercise. And I'll show you how to do this in a moment, but you can see these familiar results. The one thing that's not familiar, because I haven't done it, is that p-value. Again, I'm not going to do that by hand, because if I do, I'm going to have to use a table in the back of the book, which is not going to be adequate. So for p-value on a t-test, we're going to rely on StatCrunch. Note how large that p-value is, by the way. In section 4, we mentioned using p-value criterion, or was it section 3, I think. Section 3. When we look at p-values, we reject the null if p-value is less than or equal to alpha. So in this case, the 6872 is not less than 0.5 or 10%. Alpha was 10% for this exercise. So we're not going to reject the null. Now, one thing that 0.6872, the p-value tells me is this. The p-value, one way to think of it is this. What is the likelihood that we replicate the experiment and we get the exact same outcome or outcomes that the researchers got if the null is true? Well, if the null is true in this exercise, the average viewing time is 4.55. If you and I replicate this exercise almost 70% of times, we will get the same data that the authors or the researchers got in this case. Well, if I can replicate something 70% of times, then that's really not an unlikely event that they have observed if it can be replicated that easily, which again points to the direction or the same conclusion that the null hypothesis is not going to be rejected because the data has not proved anything unusual, contradictory to the null. So that's using p-value approach. Now let me actually go to StatCrunch and help do this for you. Let me get my pen because I need some of these numbers. I have to write them down. Okay, so summary information that we had. X bar is 4.76. The standard deviation was 2.2. These are up here. It was 2.297 and the sample size was 20. Okay, now let's go to StatCrunch and see how we get these numbers. So I'm going to go StatCrunch, X this out. Now we are in chapter 9, so I'm going to actually bring up data sets from chapter 9, and this was exercise, what, number 79 or no, number 10. This was number 101. Okay, exercise number 101. So there it is. Click on exercise 101 and this will import the raw numbers, the raw data. And these are the viewing times. There they are. So in order to run the hypothesis now, you're going to go to stat and then we're going to go to t-stats. Remember, you've been there before. You did in chapter 8, you did a confidence interval in that section or in that chapter 8. So you go to t-stats and we're going to go to one sample. And you have an option here with data or with summary. Now I'm going to use summary because we have all the important information summarized for us. But I'll come back and run it with data also because we have the data on this side. So let's go to summary first. And these are the summary information it's asking for. Okay, the sample mean that was 4.76. The sample standard deviation was 2.297 and the sample size was 20. So there you go. This is what we mean by summary statistic. It's a summary of information that the actual data points revealed. Now here we're going to test the hypothesis. The hypothesized value was 4.55 against the alternative. The alternative in this case, remember, it was two-tail alternative. Compute, and there you have it. So this is how I got the numbers that you saw, or the output that you saw in my notebook. And here it is. So this is one way to do it. Let me now show you another run using data option. So I'm going to go back to stat, t-stats, one sample, and there you go. Now I'm going to go with data because again I see the numbers here. So let's use the data. Now when you use the data, left click once on the hours, that selects the variable. And then notice there's no place for me to put those summary statistics. It's not asking me what is X bar, it's not asking me what the sample size is, and it's not asking me what the standard deviation is. The reason is because once you put in the variable, StatCrunch can figure all of those out itself. I'm just going to put the hypothesis. Hypothesized value was 4.55 against the two-sided alternative, and hit compute, and there you go. You get the same outcome. So just want to show you, you have two ways of doing it. So if you're doing homework or on the exams, so depending on what you're given, if they give you the raw data, if you see the data, then do it this way. And if on my math lab, on the exam or on the homework again, they give you summary statistics, you can also run it that way. Okay, we're done with this one. Let's take a look at another exercise. This one is exercise number 106. And in exercise number 106, this one has to do with the active management of labor. So you can read about this. It gives you an introduction to what this is about. The active management of labor, or AML here. So what I guess the gist of it is these researchers have actually used AML to see if they can reduce the length of labor actually and the rate of C-sections. Okay, but as a byproduct of this, they actually want to know if it's going to help reduce the cost of deliveries also. But that wasn't the intent. That was not the intent of this research. The intent was something different. Okay, so a cost analysis of a randomized controlled trial. That's just the source of this information, I guess, the name of the study. But right down here, I've highlighted the important information for you. According to this article, 200 AML deliveries. So that 200 becomes a sample size, correct? The 200 deliveries had a mean cost of $2,480. Now, this will be X bar, wouldn't it? Because the $2,480, that average cost, has come from 200 deliveries. So this has got to be X bar. And the deviation is also that of X bar. I'm sorry, of the standard deviation would be S. It's coming from those 200 AML deliveries. So N is 200, X bar 2480, and deviation here as S would be $766. And again, the ratio of 766 to 2,480 is rather large, which kind of tells me that average is not really a typical cost of AML deliveries. Now, at the time of the study, the average cost of having a baby in a U.S. hospital was $25.28. So this becomes the status quo. That's what the average cost was for deliveries in the U.S. hospital. At 5% significance level, remember that makes it alpha. Do the data provide sufficient evidence to conclude that on average, so that tells me we're doing this for mu, AML reduces the cost. The keywords we're looking for here, reduces the cost. Reducing something means making it less than what it used to be, right? Reducing means less than the cost of having a baby in a U.S. hospital. So all of that put together helped me formulate the statement of the hypothesis. So the null hypothesis is that the average delivery is 25-28. AML no different than any other procedure. And the researchers want to know again if it's actually helped reduce the cost, so we have less than on the alternative here. Okay. Now our test statistic, that's going to be X bar minus hypothesized mean over S over root N. That's 2480 minus 2528 divided by the denominator. So in the numerator, notice we have negative $48. So that means the average cost of delivery using AML was $48 actually less than the average US hospital. Now, the question is that $48 saving really significant? Now, once we standardize this difference of $48 divided by S over root n, we get a t-score, not a z-score, a t-score of less than 1 deviation below. That means it's not too far away from the center. So, although the sample size was respectable, 200, part of the reason they could not reject this null, or we will not reject this null, because my t-score is so low, is because the deviation is too high relative to the mean. That's why. So, again, I've drawn the distribution. This is the presumed distribution that individual AML deliveries follows a normal distribution with the mean given by the null, deviation given by the sample. And we take repeated sample of size 200, and that gives us the sampling distribution of X bars, actually going to be approximately normal in this case, 5416 deviation. Notice the deviation is not 766, so we're looking at this distribution here, X bar, 5416, and that's the center. And then once we do the test statistic, then there you go. We transform this into a t-score, and the t has 199 degrees of freedom, and this is what we have observed, negative 0.89. See how close that is to 0? So we're not going to reject this null. Our decision is, since our p-value is less than 0.05, we fail to reject the null, and if we don't reject the null, that means the AML deliveries on average do not help reduce the cost of deliveries. Now, one thing, let's see, I didn't do in this one, we didn't do our critical value, which is good. That means we get to do it together. Before we actually look at the critical value, though, this is the run of the StatCrunch, and you can kind of, we can go through this and see how I did this one also. Remember, the sample mean in this case was 2480. Right, the statement of the exercise gave us that. They gave us the deviation of $799, right? Oh, I'm sorry, $766. Right, that's this number here. And the sample size was 200, and it's 200. Okay, so let's first run this in StatCrunch, see how I got my numbers. And our alternative was less than 2528. So I'm going to go to StatCrunch in here. And this was exercise. Oh, actually, this won't be here because we don't have the data. If there's no data for it, it will not be in the list of exercises here. So I'm going to go stat, t-stats, one sample with summary. The sample mean here was $2,480 for the 200 AML deliveries. The standard deviation was 766, and the sample size was 200. The hypothesized mean was 2528, and the alternative was less than, a left tail test. That's all, and hit compute, and this is how I got those numbers. Our p-value again is large, 0.1883. So we do not reject the null, and here's the specifics of how I got those numbers, by the way. Now, the critical value that we wanted for this one. Okay, let me go back to my note, and we'll actually do this using critical value now. Let's find our critical values here. So remember, to find critical value, we need alpha, which is the significance level 5%, and the alternative is less than, right? So let's do our critical value in this case, not values, because this is a left tail test. So for critical value, again, we need alpha, and the sign of the alternative was less than, right? So this is going to be our t distribution. Okay, and we're looking at the t with 199 degrees of freedom. the center of t-distribution will be 0 here. Okay. Now, this is the critical value that we're looking for right here. Okay, and this is going to be a negative t of alpha. Okay, the alpha here is going to be, our significance level was 5%, correct? Yes, it was 5%. Sorry, I went too fast. Visually distracting, 0.05. And let me highlight this region. There you go. This is our rejection region. You see that? So I need to find a t value here, right? Now I'm going to go to StatCrunch and do this, but first let me write it. So a t of 0.05, actually a negative 0.05, because it's a left tail, so it's negative. Negative t of 0.05 is going to be, and here is, we go to StatCrunch, x. So I'm going to go to Stat, Calculators, and go down to the t. Remember, degrees of freedom for this one was 199 degrees of freedom. So let me actually put 199 degrees of freedom, and this is left tail. The area on the left you want to be 0.05. The t-score is negative 1.653. Negative 1.653. And I'm going here, negative 1.653. And that's what our critical value is. So in, again, homework or on the exam, if they ask for critical value, remember you have to get that based on alpha and based on the alternative. Those two things you need. So what did we observe here? Our t-score, there you go, our t-stat was negative call it 89, negative 0.89. So we were right in here. Negative 0.89. And note that we are not in a rejection region. True, that score is not in a rejection region. Our rejection region is this region right in here. So based on critical value approach, again, we do not reject a null. But I just want to show you how you find those critical values. Okay, so with that, we are done with section 9.5. And in fact, we are done with all of chapter 9. Our next chapter would be chapter 10. We look at two population, inferences for two population means in the next chapter. But this will wrap up this lecture for us.